Hello grade 11s and welcome to this lesson on Newton's first law of motion. We have looked at action-reaction pairs of forces between interacting objects. Now we will look at forces on single objects and how these forces affect an object's motion. Let's cross to Nelly to find out how this applies to everyday life.
Highways carry dense traffic from early in the morning right into the late evening. Huge transport trucks thunder along the roads alongside smaller passenger cars. Which of these vehicles requires a greater force to bring it to a standstill in 10 seconds? The truck or the passenger car? Which shot at the goal would be easier for the goalie to stop in 1 second? A slow-moving ball or the ball that moves at a high velocity? Hello, I'm Nelly, and in today's lesson we will answer these questions by taking a closer look at forces acting on a body. In our previous lesson, we applied Newton's third law to a number of situations. Do you still remember the law? Newton's third law states that if body A exerts a force on body B, then body B exerts a force equal in magnitude and opposite in direction on body A. This law describes the way in which bodies interact with each other and holds true whether the forces are contact or non-contact in nature. But when we want to examine and understand this overall effect of force on a body, we have to look at each of the interacting bodies separately. These are often many different forces applied to a body. We must add those forces together to work out the overall effect of all the forces acting on a particular object. For example, here is the free body diagram of the book on the table. The weight acts down with a force of 5 newtons. The normal force of the table on the book is also 5 newtons, but upwards. I can show this direction using a sign. For this example, let up be positive and down be negative. Now when I add the forces together, plus 5 newtons plus minus 5 newtons, this gives me an answer of 0 newtons. We call the sum of all the forces acting on the body or object the resultant force. Notice that neither the shape nor the motion of the book changes as a result of these forces. We say the forces acting on the book are in equilibrium. However, if the book were to fall from a height of 3 meters, there would be the same downward force of 5 newtons, which is its weight, but a smaller upward force of about half a newton due to air resistance. Do you see that there is now a resultant force of 4,5 newtons downward? This resultant force has an effect on the book. The resultant force causes the book to accelerate downward towards the floor. In this lesson, we will focus on situations where the resultant force acting on a body is 0 newtons. This will lead us to establish and apply Newton's first law of motion. We will also introduce two very important terms, inertia and momentum. We will then use all these ideas to solve the problems we posed at the beginning of the lesson. Which of these vehicles requires a greater force to bring it to a standstill in 10 seconds? The truck or the passenger car? Which shot at the goal would be easier for the goalie to stop in 1 second? A slow-moving ball or the ball that moves at a high velocity?
So from today's lesson, you will be able to state Newton's first law of motion, apply the properties of inertia and momentum to Newton's first law of motion, and discuss why it is important to wear seatbelts using Newton's first law of motion. Let's ask a question. Think about it carefully and discuss what you think with your classmates. A book is at rest on the table. Are there any forces exerted on the book that is at rest? If the book slides across the table at a constant speed, are there any forces acting on it? If there are forces acting on the book at rest and when the book moves at a constant velocity, what can we say about these forces?
Let's start by looking at what Newton's first law says. A body remains at rest or moves with constant velocity in a straight line until a resultant force acts on it. Although this may seem like a simple statement, it has some significant implications. Let's look at the two conditions described by the law. The first condition of this law says that a body remains at rest, while the second condition states that the body moves with constant velocity in a straight line. These conditions will not change unless a resultant force acts on the body. Do you think this is true? See if you can give some examples to support your answer. We'll have a look at the examples I thought of together. Look at this cart. It is not moving. It will stay stationary until I push it. In other words, until there is a resultant force operating on it. This soccer ball is placed on the penalty spot. It is not moving. A player must kick the soccer ball to direct it towards the goalie. She must apply a resultant force to get it to move. It won't start moving by itself. So it seems that the first part of Newton's law makes sense. But what about the second condition? The law states that a body continues to move at constant velocity in a straight line until a resultant force acts on it. This may not be as obvious. Have a look at these examples. This ice skater skating on ice continues to move at constant velocity in a straight line, but this car slows down quite quickly. Can you predict in which one of these situations there is no resultant force acting on the body? Well, frictional force acts on the car, which means that there is resultant force acting on the car. That is why it slows down. But there is a very small force of friction on the ice skater. This is so small, we can ignore it. We say the force of friction here is negligible, so she carries on at almost constant velocity, moving in a straight line. As a matter of fact, if you could find a piece of ice that is long enough, the skater could continue in a straight line and at a constant velocity almost forever, provided of course that there is no other resultant force that interferes with her motion along the way. So, according to Newton's first law, when we observe a body moving with constant velocity in a straight line, we can conclude that there is no resultant force acting on it. Just to make sure you understand this, let's think about it in another way. Can you remember the effects force can have on a body? Forces can bend or stretch or squash a body. Forces can cause a body to change direction. Forces can cause a body to speed up. And forces can cause a body to slow down. Now look at this special dynamics trolley that is traveling at a constant velocity in a straight line. Is it changing direction? Is it speeding up? Is it slowing down? I hope you answered no to each of those questions. But notice, there are forces acting on the trolley, the weight and the normal force. But these forces are having no effect on the trolley. This is only possible if the forces cancel each other out and the resultant force is 0 newtons. The forces are in equilibrium. I hope you can see that Newton's first law is really true, just like Newton's third law. These laws hold true in every situation. So far in our lessons, we have focused on the forces involved when bodies interact with each other, but the bodies themselves have certain properties that influence the way in which forces act, and the effect that forces have on the objects or bodies that they act on. It is on 2 of these properties that I would like us to concentrate for the rest of the lesson. The first property I would like us to look at is the property of inertia, the property of a body that keeps it at rest or maintains its constant velocity is called its inertia. It is important that you understand that inertia is a property of the body. It is not a force. It is that property of a body which resists a change in the body's state of motion. When an object is at rest, it remains at rest because of its inertia. Although inertia is not a force, the inertia of the body resists a change in its state of motion. In this case, the body. The boulder is at rest, so a resultant force acting on the body would have to be big enough to overcome the inertia of the body before it can cause the body to move. The more massive the body is, the greater its inertia. In other words, inertia is directly proportionate to the mass of the body. As a matter of fact, the mass of a body is sometimes referred to as its inertial mass. Inertia is measured in kilograms, and it is a scalar quantity. This means that we do not need to specify its direction when we describe it. When a resultant force overcomes the inertia of a body and sets that body in motion, the body acquires another property. This property of a body in motion is called momentum, and it is in exploring this property of momentum that we will find the answers to the questions that we asked at the beginning of this lesson. Momentum is defined as the product of the mass and velocity of a body. we can write a formula to calculate momentum. P equals m times v. The symbol, lowercase p, represents momentum, m represents mass, and v, the velocity. Because velocity is a vector quantity with a certain magnitude and direction, momentum is also a vector quantity. This means we have to specify both its magnitude and its direction when we describe it. Now, using the formula we've just looked at, let's calculate the momentum of an average truck moving along the highway. This truck and its load have a mass of 3,000 kilograms. It travels forwards with a velocity of 30 meters per second. Its momentum is calculated as the product of its mass and its velocity. So, we multiply 3,000 kilograms and 30 meters per second. This equates to a momentum of 90,000 kilogram meters per second for this truck. The SI units of momentum are a combination of its base units. Mass is expressed in kilograms and velocity in meters per second. So momentum has the derived SI units of kilogram meters per second. Let's check that we have completed our calculation successfully. The truck has a momentum of 90,000 kilogram meters per second. This tells us about the magnitude of its momentum. In what direction is it traveling? It goes forwards on the highway. We can give the forward direction a positive sign. So the momentum of the truck is plus 90,000 kilogram meters per second. We must interpret this sign and write out the direction with the answer 90,000 kilogram meters per second forwards. A smaller passenger car traveling at the same velocity along the highway may have a mass of 1,000 kilograms. Its momentum is calculated as 1,000 kilogram times 30 meters per second, which gives us the momentum of the small passenger car as plus 30,000 kilogram meters per second, which tells the direction of the momentum is forwards. The final answer is 30,000 kilogram meters per second forwards. Earlier we asked the question, which one of these vehicles requires a greater force to stop it in 10 seconds? Let's investigate the situation in the lab by using a model of the situation.
Hi guys, this little vehicle running down the track has a mass of 250 grams. Now we can use this to represent the passenger car. Now this one here has extra mass on it, making its total mass equal to 750 grams. Now it represents the truck, and it means it has a mass 3 times greater than the smaller vehicle. Now what we're going to do now, we're going to let each vehicle crash into the stationary barrier, and when it does that, we're going to measure the force of impact using the force sensing device. Now both cars crash into the force sensor with the same velocity, and the force sensor measures the force of impact. Now this is the force required to stop a vehicle in a very short time. The results show that the more massive car, that is the one that is representing the truck, requires 3 times as much force to stop it than the smaller car does. So it seems that the greater the mass of the vehicle, the greater the momentum, and the greater the force required to bring it to a stop.
Thanks, Aaron. That really gives us a good answer for our question. In our example, the truck with its greater mass will have a greater momentum than the passenger car, and so it requires a greater force to bring it to a standstill. Trucks are designed to cope with this fact. They have sophisticated braking systems which apply much greater force than the brakes of a small passenger car have to handle. Trucks make use of a power-assisted braking mechanism and hydraulic air brakes to bring these massive vehicles to a standstill.
You do not need to know how to calculate momentum now. You will learn about momentum in grade 12. This is just to extend your knowledge so that you have a better understanding of Newton's first law for moving bodies. You need to know about an important application of Newton's first law. Let's cross over to Nelly to find out more.
The most important safety feature in any car is a skillful and responsible driver. So before your brother or sister even thinks about buying a car, they should first ensure that they have a valid driver's license. A good place to start your research would be to page through the motoring section of the daily newspapers and car magazines. What you are looking for is test drive reports. We will look at some of the features of small 1.4-litre cars priced below 140,000 Rand. There are quite a few models in this price range. So, would a 2-door, 3-door, 4-door, or even 5-door suit you best? Is it safe for cars not to have back doors for its passengers? Well, it really depends on why you need the car. If you transport very young children, it could be better to buy a 2-door car, as your little children won't be able to open the doors while you drive. But if your car is involved in an accident, it's easier to help passengers out of a 4-door vehicle, and most modern cars have a safety catch on the door locks that prevents the passengers from opening the doors from the inside. These child locks are standard in most new cars these days. Then, there's the issue of boot space. Buying a sedan ensures that you have a boot in which to put the luggage. But the rear door of a hatchback allows these cars to be used as multi-purpose vehicles. The back seats fold down, giving ample space for you to move small pieces of furniture. Just remember that it's not safe to transport passengers with the back seats folded down. It is illegal in South Africa to transport passengers, even passengers in the back of the car, if they don't wear their seat belts. You should know by now that this is a sensible law. If the passenger doesn't wear a seat belt, he continues to move forward when the car is brought to a sudden stop. He only stops moving when he hits the windscreen or the seat in front of him, and a collision of the passenger and windscreen is very likely to cause serious or fatal head injuries. Can you remember what the scientific explanation is for the motion of a passenger that does not wear a seatbelt? Newton's first law of motion states that a body will stay at rest or will continue to move at constant velocity in a straight line unless a resultant force acts on it. It is the property of inertia of the passenger's body that maintains his motion at a constant velocity. It is little wonder then that the seatbelts in modern cars are called inertial seatbelts. Let's take a closer look at how these seatbelts work. When the car stops suddenly, the passenger continues to move forward with the same initial velocity. The passenger's chest exerts a sudden sharp jolt on the seatbelt, which responds by locking the belt tightly so that it holds him securely in his seat. This ensures that the passenger slows down at the same rate as the car does. Small children should be transported in a child seat, which is strapped into the car using one of the seat belts. It is when you need to apply brakes suddenly and sharply that people really appreciate the action of their seatbelt. The other question which we wanted to investigate is, will it take more force to stop the faster moving soccer ball or the slower one? What do you think? Do you think that there will be a similar relationship between velocity and momentum as there is between mass and momentum? In this demonstration, we have a slow-moving ball rolling towards a thin piece of cardboard. The ball comes to a stop when it hits the cardboard. Now we have a faster-moving ball rolling towards the same piece of cardboard. It doesn't stop as it hits the board. If we repeat the experiment with a thicker piece of cardboard, the faster-moving ball does stop.
So think about this experiment. What is the relationship between velocity and momentum? And will we need a bigger force to stop the ball that has the higher velocity? You will find the answers to this question in the video on Newton's second law of motion. Remember to visit the Mindset website www.mindset.co.za/learn. Until then, goodbye.
Body. We must add those forces together to work out the overall effect of all the forces acting on a particular object. For example, here is the free body diagram of the book on the table. The weight acts down with a force of 5 newtons. The normal force of the table on the book is also 5 newtons, but upwards. I can show this direction using a sign. For this example, the ball that moves at a high velocity. Hello, I'm Nelly, and in today's lesson we will answer these questions by taking a closer look at forces acting on a body. In our previous lesson, we applied Newton's third law to a number of situations. Do you still remember the law? Newton's third law states that if body A exerts a force on body B, then body...
How this applies to everyday life.
Highways carry dense traffic from early in the morning right into the late evening. Huge transport trucks thunder along the roads alongside smaller passenger cars. Which of these vehicles requires a greater force to bring it to a standstill in 10 seconds? The truck or the passenger car? Which shot at the goal would be easier for the goalie to stop in 1 second? A slow-moving ball or B exerts a force equal in magnitude and opposite in direction on body A. This law describes the way in which bodies interact with each other and holds true whether the forces are contact or non-contact in nature. But when we want to examine and understand this overall effect of force on a body, we have to look at each of the interacting bodies separately. These are often many different forces applied to a
Hello grade 11s and welcome to this lesson on Newton's first law of motion. We have looked at action-reaction pairs of forces between interacting objects. Now we will look at forces on single objects and how these forces affect an object's motion. Let's cross to Nelly to find out